My name is Isaac Berry from Berry Science Lab, and welcome to lecture number 1 of electromagnetism. So what is electromagnetism all about? Well, electromagnetism, as you might have expected, is a course studying how electricity and magnetism are related. Now, what is this course actually going to build up to? Well, unlike other courses, we can actually say it straight, here, right now. What are we going to build up to? There are these things called the Maxwell equations. And they describe how any electric field, like the current flowing through a wire, can actually generate a magnetic field, and how that magnetic field can also generate its own electric field. So, what are these Maxwell equations? What do they tell us about the relations between the electric and magnetic fields, or electricity and magnetism? Well, let me write them out right now. Number 1, number 2, I'll write this in short form, number 3, and I guess I'll add vector signs, number 4. All right, there we go. These are what we're building up to. But now you're probably really confused. What does half of this notation even mean? So let's start with the very basics of electromagnetism. Because to understand what we're actually building up to, we have to understand the notation inside it first. So the basis of electromagnetism is vector calculus. So what is vector calculus? Well, that's a very good question. You might recall, well, you should recall, that in single variable calculus, we take a function f that maps real numbers to real numbers, and we define a whole bunch of things with this function. We define a limit, we define a derivative, we define an integral, we can define a whole bunch of things using this function. But now vector calculus takes all that and says, hey, what if instead of mapping from R to R, I mapped from some number of dimensions m to some number of dimensions n? In this case, the electric and magnetic fields are both functions that map from R3, which means the space that we all live in, three-dimensional space, to R3. But what does that actually mean? What are vectors? Well, hopefully you know that because you're in electromagnetism. Three-dimensional vectors are just arrays of three real numbers. And these symbols almost signify a kind of multiplication going on between vectors. So you can add two vectors, and you'll probably get a very expected result, which is another vector, but each component is the component of the previous two added. And you can also subtract vectors, and instead that's just going to give you what you would get if you added the negative version of the second vector. So addition and subtraction over vectors is quite intuitive. But then we come to the subject of multiplication. How do we define multiplication here? Now, your instincts might take you to or we'll use more sleek notation, x1, x2, x3 times y1, y2, y3. Well, that should just be equal to x1, y1, x2, y2, x3, y3, right? Now, this does satisfy commutativity, and this does satisfy associativity, but it's not linear. And even worse, it's not distributive. Which means it has basically none of the useful properties that we want out of a multiplication operation. So instead, we've defined two different methods of multiplication. Number one is the dot product, which is actually very similar to this, but it gives you a scalar, which is the sum of these components instead. And this actually works way better because now this is distributive and linear, unlike the previous. And then there's the cross product, because you might be tipped off by the fact that multiplying two vectors doesn't get you another vector. Well, I mean, that feels useless then, doesn't it? Oh, and one nice property is that if the dot product of two vectors A and B is equal to C, then C is equal to the magnitude of those two multiplied by the angle between them. Well, cosine of the angle between them. And similarly, if A cross B is some vector C, then that vector C is going to be equal to, actually I'm going to use D for no confusion, the magnitude of A, the magnitude of B, or the magnitude of D, will be the magnitude of A, magnitude of B, sine theta AB. So, now what is the cross product? Well, let me unveil its formula in all of its unholy glory. So, we start x2y3 minus x3y2, comma, x3y1 minus x1y3, x1y2 minus x2y1. Pretty sure that's it. Isn't it beautiful? No, it's not. So you might ask yourself, well, why is it so disgusting? I thought its only goal in life was to achieve this. Well, here's the thing. This gains a geometric interpretation when you start graphing vectors. Because if you graph these two vectors in the 3D plane, what you might not get is that there's actually only going to be one vector that's perpendicular to both of these. One direction that's going to be perpendicular to both of these. That actually makes infinitely many vectors. Why? Well, I mean, think about the circle of vectors that's perpendicular to, let me just move this. Think about the circle of vectors that's perpendicular to this guy. So the circle of directions that can be perpendicular to this guy looks something like this. Like a disc with this guy protruding straight out of it. And the same thing for the other vector. And those two disks only collide along their diameters in one specific direction. That's what the cross product means. It's the unique direction such that it's perpendicular to both vectors in the product at once. Now, I want you to ask yourself for a minute, when is the dot product of two vectors equal to 0? Well, either one of their magnitudes is equal to 0, which means one of them is a 0 vector, which is not very useful, so we disregard that. But the other case is when cosine is equal to 0. And when is cosine of something equal to 0? Well, either when it's positive pi over 2 or negative pi over 2. Which means that if the dot product of two vectors is equal to 0, then the angle between them has to be 90 degrees. And as a consequence, you'll realize that since the cross product of a vector is perpendicular to it, you'll get that A cross B dot A is the exact same as A cross B dot B because it's 0. Also, do note that unlike the dot product, which is commutative, multiplication or cross multiplication is not commutative. It's actually anti-commutative because A cross B is equal to negative B cross A, which you might have guessed from its full expansion. So, now you know what the dot and cross symbols here mean. But you might be wondering, oh, and just for reference, E is electric field. Don't feel like drawing that. And B is the magnetic field. Okay. So, let's cross off the list of things we already know about. So, we already know what this is. Okay, that's crossed off. We already know what this is. That's crossed off. We don't know what this is, but that's a physics thing, not a math thing. So that's crossed off. We already know what this is and what this is, so that's crossed off. Actually, we do have to get to that first. But we know what this is and we know what this is, so that's crossed off. And we know what, actually we don't know what this is either, but we know what this is and we know what this is, so that's crossed off. So let's circle all the things we don't know about. I'm seeing an eerie pattern. So, first, let's cover the secondary thing. What is this? Well, here's the thing. This is an abbreviation for this. Now, what is that? Well, it might be more recognizable as an analog to d dt, which is the time derivative of a given function, f of t. But why the curly d? Well, because it's not a single variable derivative anymore. You might recall that in 3D, we have to deal with functions, often we have to deal with functions of 2 variables instead of just 1. And those start to look like these surfaces. Things like this. And now you have to ask yourself, well, what do we do with these surfaces? Because for a single variable function, if someone asks you to take the derivative at this point, you know they mean, well, zoom in on the function, take 2 points that are really close together, take their secant line, and then just keep drawing them closer and closer. And of course, the way they have to get close has to be along the x-axis, or along the y-axis if you're taking dx dy, but that's just 1 over dy dx. But that's totally thrown out the window for surfaces, because with a surface, if I tell you find the derivative here, well, what direction should the other point be approaching it? Here we can just say it's f of x plus h minus f of x over h. Over here, we can't divide by a vector. And even worse, what direction is h in? Is h in this direction, this direction, this direction? Where is the second point for our secant line approaching from? These the full solution to that is called directional derivatives, and I don't think we'll need to get to that in this course, but the partial solution to that is called a partial derivative. Now, what does partial xf mean? Well, you probably guessed it. That's how the function changes if you only look at it along the x direction. So, if you keep y constant, and you only focus on how the function changes in the x direction, and then you pick a particular point, then you can tell me, okay, move the second point in this direction, and I can find the derivative for you. If you want a geometric meaning, it's kind of like taking the xz plane and the cross section of that with the surface, and then finding the derivative at a given point of the curve formed by that cross section. Same thing with y. And you've probably guessed that with partial t of some given function f, we want to know how that function changes not over space, but strictly if we choose a specific point in space, how it changes over time. It's like instead of going around the world and filming a video trip, it's like you just set up a camera in front of one park bench and you film how it changes over time. Instead of changing over space, you're looking at what's changing over time. So that's what partial t means. So we can cross that off the list of things we don't know. So finally, what is this nabla thing? Why is this vector so prominent? Well, it's not actually a vector. Now that sounds stupid, right? Because then why are we using this notation? But vectors have to be arrays of real numbers. Nabla looks like this. None of these three, as you might notice, are real numbers. They're all partial derivatives, but they're conspicuously missing one thing, a function. So this seems to be nonsense. But just hypothetically, say it wasn't nonsense for a second. Then say you had a function f, which is equal to fx, fy, fz, the vector components. Now, for a second, pretending none of this is nonsense, calculate this dot product. It's partial x fx plus partial y fy plus partial z fz. But that one makes a lot more sense. This is an actually tangible physical quantity. So this is just our abbreviation for this much grosser term. But this actually has a geometric meaning, although we'll get to that next time. And similarly, the cross product acts in the very same way. I'm not going to write it out here, but it's going to be something like partial y fz minus partial z fy, then comma, it's a vector, partial z fx minus partial x fz, and I'll keep to my promise of not writing it out. So there we go. Now we know what this nabla means. It's not a real vector, it's just an abbreviation for something much nasty. If you want, you can also call this divergence, and this curve. So if you want no nonsense in your Maxwell equations, you could very well erase all of this and instead write div E, div B, curl E, curl B. But it just doesn't feel the same. Now you can understand that these two are so intricately affected by one another. In fact, the electric field's divergence is only affected by itself, since this is charge density, and the magnetic field's divergence is constant. But as you can see, the curl, and yes, this name means something, of the electric field is heavily dependent on the change over time of the magnetic field. And similarly, the curl of the magnetic field is heavily dependent on not only the current, which is part of the electric field, but also the direct change in the electric field, which shows just how intricately electricity and magnetism are connected. So next time, we'll start our track on deriving these equations, which are the end goal of our series. So that's it. Thank you for everybody for watching.